I was curious, one of the projects that you guys worked on, the MSG Sphere in Vegas, obviously a very fascinating venture. Can you tell us about Cast Connex's involvement in the project? And then obviously, I'm sure you had some unique challenges with that one. I would love to hear about them.
The MSG Sphere is a one-of-a-kind structure. It's the world's largest spherical structure, and it's supporting a very high-resolution, enormous LED screen mounted on the exterior. And with these LEDs, the way that they're installed, you can probably imagine that geometric tolerance on the supporting structure is critical, because if the geometry is off, then if two of these LED panels get a little too close, you get like a bright line. And if they're a little bit farther apart, you get a black line. And so there was a much tighter geometric tolerance on that exosphere.
I know you've seen the Las Vegas MGS Sphere, the one with all of the LED lights, and I'm excited today because we're going to be talking to the steel connection engineers that designed that. We'll be talking to Cast Connex Corporation. We'll be talking with Carlos D. Oliveira, the Chief Executive Officer, and Michael Gray, the Executive Vice President. They're the co-founders of that company, so I'm very excited to go talk to them. I'm your co-host, Matt Picardle.
And I'm your co-host, Rachel Holland. And this is the Structural Engineering Channel.
Carlos and Michael, thanks so much for joining us today. Could you tell us about what you do on a daily basis and what your company is all about?
Sure. So I'm Michael, and basically, Cast Connex is a company that Carlos and I founded. We specialize in using casting technology to solve problems that are faced by structural engineers, often in steel construction, connection details, sometimes with timber, sometimes steel and concrete working together. But what we do is we use our expertise in both structural engineering and the design of steel castings to leverage the freedom of geometry and freedom of sort of material properties to develop solutions that can look better, work harder, be easier to fabricate or erect for structural framing systems.
Carlos, you want to add to that?
So, well, on a daily basis, you can think of Cast Connex as we are a product supplier, but we are in practice connection design engineers, just with very specialized capabilities. So we engineer and design the components that we manufacture and deliver to steel fabricators. So oftentimes designers wanting to leverage casting manufacturing in their projects for whatever reason, be it architectural or functional, they would engage us to design and supply those components. And ultimately the connection design of those components would be delegated to Cast Connex, and we would carry out that design and then supply the components most typically to the structural steel fabricators. So our day-to-day is kind of specialized connection design.
Are you guys both engineers and both had like previous experience in cast design, or is like one of you the expert in one thing and one of you is the expert in the other?
We're both structural engineers. We met doing graduate research on steel castings, like novel steel castings. And so our projects were very closely linked. So we come from a very similar background. I wouldn't say that one of us is really the expert versus the other.
Now we should say Michael has his doctorate, so he's Dr. Michael Gray, and I only did a master's degree. His doctorate actually followed from my master's research. So, you could say I was the first, but he's the doctor. So.
Okay, excellent. What about, so starting, this is obviously like some disruptive technology. That's a bold move. So tell us more about the story of how this company was created and, even some of the challenges that you had to face and overcome.
Well, so when we were doing our research, it became apparent that there was a commercial potential for what we were working on, right? And I think it's because we both came from some practical experience, even as grad students, through co-op and work experience. And so when we were developing the solutions, we were really focused on what would be practical within the context of how the industry works and what would be practical from a casting and foundry perspective from what we knew and understood and had learned about that. And I think that led to the idea that there could be commercial potential. Now, we had originally thought, this is an opportunity to get, maybe license the technology and get a few bucks for doing a grad degree, and that would be a big win. But what we found was that there wasn't really a market player at the time that was positioned and interested in kind of taking this on. Like, we got a lot of positive feedback about what we had, but it just didn't fit within any of the sort of companies that we talked about within what they were doing. And rather than kind of give up on patent applications and everything we'd already done to that point, we decided, well, maybe we should start our own business. And with the help of our advisors from the University of Toronto, Dr. Packer and Dr. Chrysopoulos, we founded Cast Connex when then we were kind of sought out some small investment money and government support from the Ontario government to actually start the business. Now, having said that, Cast Connex and starting a business in the construction industry is not like a typical tech startup. I think, we didn't hire 100 people and just start, losing money and working on some kind of like pipe dream. It was very slow, right? In our industry, a brick has been a brick for 10,000 years or something like that. So we needed to really pace ourselves. And one of the best lessons we got from one of our early advisors was to sell a little and learn a lot. And I think that mantra has really paid off. We did benefit from finding early adopters, which can be challenging in our field. Not everyone is kind of tuned into trying something new when they're on tight budgets and trying to just get the design done. But luckily we were able to identify those people and get our start and grow through some really kind of early learning experiences, I guess, to the company that we have now.
You mentioned that you guys met up in grad school and that was how this sort of all was born. But what originally inspired you to focus on the steel castings?
That was mostly our research supervisors. So when I started my master's degree, I wanted to focus on structural steel, and I was interested in connections and perhaps seismic design. And two professors at University of Toronto both had those backgrounds. And so I approached them and talked to them about what potential projects they might be working on and, how I might be able to assist on any of their research projects. And they kind of came up with the idea for us to look at cast steel connections for use in seismic resistant connection design or seismically loaded structures. And so, Jeff Packer is very renowned in terms of tubular construction and HSS connection design. He was one of the supervisors, and he suggested, well, why don't we look at connections for HSS bracing in seismic resistant braced frames? And of course, Konstantin Chrysopoulos, being an expert in seismic design, was a really great co-supervisor for that research topic. And so through trying to solve the challenges associated with connecting a hollow section brace into a gusset connection in such a way that you won't fracture that connection in an earthquake, we were looking at how casting manufacturing could be leveraged to address that challenge. And ultimately, it was through that research that we started to really clue in on, the capabilities of casting manufacturing to address not just seismic resistant connections, but many other challenges faced in steel design and steel connection design.
And so for steel casting, what are some of the benefits of that? I guess what makes that different than just the regular structural engineer just specifying an HSS to HSS weld connection, right? So what are the benefits, and I guess why one of the key factors on why your business is striving in terms of steel castings? What is it about the steel castings that helps everyone out?
With steel casting technology, we have a much broader availability of potential geometry, right? We can sculpt the casting however we see fit within the limits of casting manufacturing, which is pretty liberal. What that means is we can put the material where it ought to be for the flow of forces. We're not restricted to taking some kind of rectangular shaped plates and trying to weld them together to build out what we need. So we can have material efficiency in some cases, or we can improve fatigue performance in some cases, or we can make a shape that is just, that much better looking in a lot of cases. So these are some of the key values that casting technology can bring. We can choose materials that are suitable. In my research, I was looking at yielding elements. So I was basically trying to design a ductile fuse for a brace frame, so where the casting is doing the yielding. And you would think, okay, castings are brittle, but you're thinking of like iron castings. We're designing a steel grade and material to maximize ductility, and we can shape it in such a way to really promote and get the most out of it. And so that was how we were able to kind of engineer this component that was relatively small but had an enormous amount of ductility within it. So it's that freedom to choose materials, to choose shape appropriate for the structural purpose that is very unique.
When you guys cast, so I'm not totally familiar with like that process of just casting, but do you get to have like a say in like, well, I mean, obviously you get to pick what kind of steel is being cast, right? But do you get to pick like the properties of it then? Like, do they make it specifically for you kind of a thing? How does that work?
Yeah, so we're the casting manufacturing process, you melt scrap steel and then you add alloy to it to bring it to within a certain chemical specification. You can also heat treat after the component is solidified. So the combination of the chemistry and the heat treatment is really what dictates the mechanical properties that we can achieve. So the fact that foundries are able to small batch steel in that way, where we start with really, kind of vanilla, if you will, in terms of the scrap steel material, and then can alloy it in really any way, it enables us to produce cast steel grades that can have any wide range of mechanical properties. So typically when we're designing components for your typical structural application, we're using, low alloy cast steel grades, but we could produce high alloy grades. We can produce stainless or super duplex stainless steel grades as well. So we also have that freedom of mechanical properties, really, in addition to geometric properties, so that we can leverage both in our design of the components.
Interesting.
Yeah, that's pretty cool. So it seems like you're in control of not only the materials and how it's shaped, but then you're also responsible for the design, which involves the nonlinear finite element analysis. So kind of the whole package. Could you go into what the analysis process looks like for you guys in these types of connections? It seems pretty custom.
Yeah. When we're getting involved in kind of like one-off custom castings, we start with shaping it based on whatever the inputs are, framing angles, member sizes, architectural intent, and we try and develop an exterior geometry. And then we, carve out, if it's hollow, what are the wall thicknesses? What do we need to maintain in order to have a sound casting? Because shaping a casting is more than just having it shaped for its final use. But we also, remember, we're pouring steel basically into a hollow void that is the shape we want. And that, steel has to fill that cavity as quickly as possible with as smooth a flow as possible to avoid, any kind of defects or air or sand getting into it as much as possible. And it needs to solidify in a way that is as sound as possible. Because you can imagine when a casting goes from liquid to solid, it's going to do so from the coolest parts into the hottest parts, which is basically usually from the outside into the thickest component. Now, if we can shape it in such a way that we can drive that solidification, we can avoid a lot of the shrinkage that would occur during the volumetric change between liquid and solid, because when it freezes, it kind of shrinks. And if it's the last part to freeze is the middle, then you're going to get kind of a spongy center, almost like when you bake a cake, right? And you get that sponginess in the middle. That's kind of what will happen here. So we try and shape it for the manufacturing process. Once we have all that determined, and obviously that process is also informed by the loading, then we're going to take that model of that component and we're going to run usually a nonlinear finite element analysis. So there's a lot of coordination with the structural engineer of record, because we'll need equilibrated load sets and data, and we'll pull that in with our own model and then run that analysis to generate our engineering calculation package.
Interesting. That seems like a lot to go into all of that. It's just like just such a different thing to me. So, okay. So I was curious, one of the projects that you guys worked on, the MASc sphere in Vegas, obviously a very fascinating venture. Can you tell us about Cast Connex's involvement in the project? And then obviously, I'm sure you had some unique challenges with that one. I would love to hear about them.
The MASc sphere is a one-of-a-kind structure. It's the world's largest spherical structure. and it's supporting a very high resolution, enormous LED screen mounted on the exterior. And with these LEDs, the way that they're installed, you can probably imagine that geometric tolerance on the supporting structure is critical, because if the geometry is off, then if two of these LED panels get a little too close, you get like a bright line. And if they're a little bit farther apart, you get a black line. And so there was a much tighter geometric tolerance on that exosphere than you would see in a normal structure. And of course, it's a highly constrained structure, right? A lot of the nodes had, I believe, like 8 nozzles on them. And so any kind of geometric issue in those connection points would start to throw off the structure as you're erecting it, and you'd start to move away from that perfect sphere very quickly. The nodes that we developed, one of the key advantages is they're CNC machined within a 1/32 tolerance of each nozzle on each end. And so that allowed for a very precise geometric control during the installation and erection of the sphere, which obviously in turn made it possible to actually get those LEDs on there within the required spec tolerance.
Interesting.
Now we did something similar on the inside too, because there's also an even higher resolution screen on the inside. So once the outside was going up and seemed to be going well, we kind of got involved in providing cast node connections also for the inside to make that inner screen work out.
That's so unique.
And what was, well, just even with that, was there things about like shrinkage in terms of, because the construction tolerance was so tight, was there any shrinkage problems with the concrete or expansion, or was that already taken into account with everything during construction?
So there was a lot of attention paid to this structure as it was erected. I think at least twice a day, right, Carlos, the structure was surveyed in order to make sure that as it was being erected, it was going into the shape that it needed to be. So there was like a whole approach for shimming the connections. So the connections on the ends of the nodes were like end plate bolted flange connections between hollow sections with plates on the ends, and then our cast node. And there was a variety of like optional shims that could be used in that joint to help adjust to get it into shape. But as you can imagine, the desert, which has a huge range of like thermal like temperature between the morning and the afternoon. And so there's a lot of care was put into surveying in order to make sure that as they're building it, it was going into the proper shape. I can't give away too many secrets, but let's just say that was very important.
Yeah, and we have to acknowledge Severed, the structural engineer of record on that project, did a spectacular job, and SDL were the erection engineers for W&W who fabricated and erected that structure, and it was an incredible venture. Had incredible teamwork to be able to make that happen.
Did you guys get to go to a show there like immediately after the opening? Was that part of?
We did get to go to a couple shows.
Great.
Yeah. We've been to a couple shows.
Yeah, just pointing up and seeing, oh yeah, I remember that one.
And it is totally worth the hype. Everyone should go check it out. Yeah.
Yeah, I haven't gotten to go inside yet, but from the outside it is really incredible. So nice job on that one.
What was it like even getting that project? I imagine you get this project that's pretty unique, and then I know it's not like cookie cutter one. Do things just keep going off in terms of, oh yeah, we can do it this way, we could do it this way for that type of project?
Well, what often happens in our work is the engineer of record on a complex project like that might reach out to us because they're familiar with our capabilities and they know the challenges that they have on their project, and they understand how our approaches or manufacturing capabilities might assist them. And so in that particular case, the engineers at Severed did reach out to us during the design phase as they were developing potential connection concepts for the sphere. All of those nodes in the sphere really were conceived of as either fabricated connections or as cast connections. And ultimately, 2 parallel designs were developed on that project. And they left it to the contractors who were steel fabricators to decide whether or not to fabricate the connections or to leverage our cast steel solution. And ultimately, W&W, who are very capable structural steel fabricators, saw the merit in this in the casting solution in terms of the dimensional tolerances that we could deliver in the connections, and how our solution would enable and simplify their shop fabrication activities and their field direction activities, and reduce risk and ultimately save cost on the project.
W&W had, like, at the time, they saw the value in what we were presenting, and it was interesting. At the AISC's NASCC conference that year, Bill Lindley of W&W, is he their chief engineer? Is that his title? Wanted to meet up with us and just kind of looked us up and down, and was like, because we didn't have a lot of experience with them. And I don't know, he just kind of shrugged and was like, okay. And that was it. I don't know what he saw, but yeah, it worked out. And like, we're very grateful that they took that chance. Because, I mean, like you asked, what was it like winning that job? When we found out that we were going to be on it, it was like one of the probably top 3 moments in our company history, right, Carlos? Like, if not the top.
That's so cool.
Yeah.
So awesome.
Yeah.
Yeah, and a quick plug for engineers wanting to go to that. I know the NC-SCA conference, I believe, is going to be in Vegas. So for me, I'm going to that one. So I definitely want to stop by and visit that one. That's the thing I always see.
Yeah.
I always see the spear somewhere, somehow. So it's yeah.
There will be a tour and a talk on the project, as well as part of the NC-SCA program. So certainly, if you haven't registered already for the conference and also for the tour, you need to do that, because I believe that their space is limited.
Thanks for the reminder.
All this talk, Matt, about wanting to go, and you're not even going to get in time.
Yeah. Now that there's a tour, yeah.
You might have an inside. You might have an insider that can sneak you in. I don't know. You might have to.
Interesting. Okay.
Yeah.
Okay. But besides that one, I know you guys worked on some other ones. I know the Mobile Launcher 2. I believe that's the NASA's Artemis program. Could you get into that one? I know that one had some pretty unique challenges as well.
Yeah, so just as we were wrapping up our work on the sphere, and we were wondering, how are we going to top working on the world's largest spherical structure, the phone rang, and Mark Holland of PVS was on the other line, and he said he was working with NASA and Bechtel on the design and construction of Mobile Launcher 2, which is, as part of the Artemis program, NASA will be launching the most powerful rockets ever launched off of Earth to put people back onto the moon, and then with lessons learned from that, they will eventually put people on Mars with rockets launched off of Mobile Launcher 2. And so PBS reached out to us because they had some really big challenges with complex connections on that launch tower. Mobile Launcher 2 is a larger tower. It had to be obviously stiffer and stronger than Mobile Launcher 1 because the rockets are getting larger, but ultimately all of the existing infrastructure, from NASA's existing crawler mechanisms to the existing crawlerway, from the vehicle assembly building where the rockets are put together and built on top of Mobile Launcher 1, and then Mobile Launcher 1 is rolled out to the launch pad from which the rockets are launched. All of that existing infrastructure was all designed and constructed as part of the Saturn V rocket program, and is weight limited based on all of those existing smaller rocket and infrastructure. And ultimately, here we are having to use all of that same infrastructure to launch more powerful rockets. But with those weight limitations and the structure having to be stiffer and stronger, they had some pretty significant challenges with the structural steel connections. So they reached out to us to see if our solutions and our approach to being able to optimize material efficiency would offer a way for us to make connections that could resist all of these higher forces, but wouldn't be too heavy such that infrastructure would be overloaded by the larger rocket tower. And so, ultimately through some preliminary study exercises, we found that in fact, yes, we took some original connection designs that were fabricated connection details, and we showed that we could make connections that were stiffer, stronger, and lighter. And so ultimately that's how we were engaged to design and supply all of the connections on that mobile launch tower.
And was that utilizing custom connections in terms of the casting process and doing the finite element analysis, essentially getting everything down to maximum efficiency, like something that can't be really achieved that well with your typical connections. It's right. It has to use that.
Yeah. On the outside, these connections, you might look at them and you might think, oh, they just look like a tube to tube connection. But ultimately what's happening on the inside is there's variations in wall thickness, and there's openings and other features on the inside that really just could simply not be fabricated. These transitions from thick to thin, internal stiffening and strengthening in certain areas where it's lighter in other areas. Ultimately, you just simply could not have made connections that were lighter than what we achieved, and yet stiffer than the fabricated alternative and capable of resisting the loads that were applied to them. It's just not feasible to do that with conventional fabrication, where you're just trying to cut and shape plates and weld them together. Our method of design and analysis is just cannot be matched in that regard.
That's cool. Yeah, it's a typical structural engineer tries to specify that with different wall thicknesses. The fabricator would just be like, "What are you guys doing?"
Yeah, well, and it would have been very complicated TYK welding between those adjoining tubular elements with overlapping welded joints. It would be very difficult to control the tolerances. And like you said, like you'd have to increase the wall thickness in these connection zones such that the connections don't drive member selection. Remember, they're trying to minimize the weight of this tower, so they want to utilize the members themselves as high as possible. So say you have a tension member, you want that thing loaded up to 0.9 AFY of the tension member, but then you get to the connection and you can't physically connect it for those forces when you have all of the overlapping forces from all of the members. So we're able to design a very complex nodal connection that accommodates a number of members framing into the single joint, and ultimately just enables like a complete joint penetration weld at a distance away from this very complex geometry of the node kernel. And then ultimately that node kernel is lighter than you could ever fabricate it to be able to do the work it has to do.
And I guess for my follow-up question is, in terms of how that works, it's essentially the structural engineer of record will design the main thing, but then when it comes to those connections, that's when they may recommend you or the contractors recommend you to take a look at it. That's where you kind of step into the picture, right? To kind of just see what the best type of connection is.
Correct. Yeah. Like in your typical design bid build, especially outside of, say, the West Coast, your steel connections are going to be delegated. The connection design is often delegated to the fabricator. In this case, these connections are very complicated, and they might not be able to be achieved without casting manufacturing, or maybe the architect and engineer would like to leverage castings from an architectural perspective. And so in the contract documents, they'll call out a joint and they'll say that's a cast steel connection. But ultimately, the design and manufacture of those components is delegated to typically the steel fabricator, and then the steel fabricator would hire us to actually engineer and manufacture those components under contract with them.
Cool.
So this NASA project is still underway, right? It's not completed?
It's currently under construction, yeah.
Okay, so you you were wrapping up the sphere, you get this phone call. So another obviously very big, exciting project. What's next? Where do you see the future of steel castings, and how do you envision it evolving for the coming years? Who are you hoping is going to call you when this job wraps? What's the next big exciting thing?
Well, I mean, we get excited about all our projects, and we have lots of projects that are, I guess, in some ways more conventional buildings, but still very exciting projects. And they're all kind of on the go continually. I think one of the big things that's on the horizon is, we've gotten to a point where instead of the kind of pushback on castings, a lot of the industry players now understand in some way their value or when they should be considered. We're getting calls from contractors to bring us into projects where there's complexity that we can address, which is an exciting kind of new step change. Instead of just the engineer saying it, sometimes the steel fabricator is kind of pulling us into really interesting opportunities where we can use our skills in optimization and shaping. But one thing on the horizon is the idea of this additive manufacturing, right? 3D printing of steel. The technology has really started to come forward there. There's some really amazing things being done. And really the challenges and the approach are not that different than those that we are already facing or have already figured out a formula for with steel castings. 3D printing allows free form geometry that's going to require nonlinear finite element analysis to design it. Same as a casting. 3D printing is a new material that maybe isn't as familiar with engineers, maybe isn't as crystal clearly called out in the code, much like castings when we started. Understanding the potential non-destructive examination that we want to perform on a casting and how it could apply to a 3D printed element there's parallels. So there's loads of parallel between that additive manufacturing with casting, and we see that as another avenue for us to expand our skills and help our industry continue to evolve, continue to adopt new technologies, and be that disruptive kind of change maker.
In terms of structural engineers that are looking at career paths in structural engineering, I mean, is this more of the specialty type of career path when they're doing, right? It's not your typical structural engineering job. It seems a lot more specialized. I'm guessing you guys hire structural engineers that specialize in this nonlinear analysis. Like, yeah, what's it like where structural engineers can fit in for this type of special analysis?
Well, the first thing that I'll say is that, both Michael and I are structural engineers, and, we did civil engineering undergraduate degrees and then went on and studied structural engineering in grad school and then created Cast Connex. But that basis in structural engineering is applicable in everything that we do. We're highly specialized. We're specialized connection designers and product engineers, but we hire structural engineers that work in our department. Obviously, they don't come to us just fresh out of undergrad or from a master's or doctoral work with a full understanding of casting manufacturing or full capabilities in terms of finite element stress analysis. But if they have the fundamentals in structural engineering and understand generally steel construction and fabrication and interaction, then they have the basis to join our team and to learn about casting manufacturing and to learn how to analyze structural connections using finite element analysis and how to interpret those results in the context of the AISC code or other codes that we work in. And so, our team is structural engineers that learn about manufacturing and how to design for manufacturing.
Very cool.
For being, I think you guys are kind of unique, right? In that you're both structural engineers, but you also had that entrepreneurial part of you, so like for younger engineers that also have that, like, a success story to help keep them motivated, right? Like, you started out 2 people in grad school, and it's been how many years and how many employees do you have now? Like, I know it's a slow growth because of just what it is, but what's that?
Well, so I guess we've been at it for 17 years, Michael, is that about right?
Yeah.
We've done hundreds and hundreds of projects all over the world, mostly in North America, but globally. We've put over 100,000 steel castings into structural service in various types of projects, everything from residential construction up to multi-billion-dollar transit terminals or rocket launch towers. In terms of our team size, we're a small but mighty team. Primarily, we, on a functional basis at Cast Connex, we're carrying out all of the design and oversight of manufacturing. We subcontract the manufacturing of the components that we produce. We subcontract to steel foundries kind of located all over the world. We put people in those facilities to oversee the manufacture of the components that we're manufacturing and delivering to our projects. And so, whether you look at it directly or indirectly, we're employing hundreds of individuals in design and manufacturing to produce the components that we supply into projects. So it was incremental. It is still incremental. And it's been a long and hard process, but we're very proud of what we've built. And, I'd encourage others who are interested in pursuing entrepreneurship to really go for it. I mean, if you don't take a chance, and keep in mind, we're from Canada, so I have to use a hockey reference here, but you miss 100% of the shots you don't take, right? So just shoot at the net and, maybe it'll go in.
And Do you have any final piece of advice? I know, Carlos, you want to add another one, but maybe Michael can chime in too. Any final piece of advice for
it's going to be another
young
hockey
engineers?
No, I'll refrain from hockey cliches, but I think like going back to, when we started, like, and at the beginning of this, I mentioned, we kind of had this idea that, we'll just get some money for some patents and we'll go on our way with the career path that we had basically laid out since we started our undergrad. Being open to changing was an important part of being where we are today. And as engineers, we like to have plans. We like to have kind of a defined kind of route, but having an open mind to the idea that other things are possible and taking opportunities when they come, I think is something all like young, students or recent grads should keep in mind, because there's a lot of opportunity out there that you might not have realized or maybe thought would be possible. I often, if I volunteer at the university for talking with students about entrepreneurship, the feedback I get is that, I'd like to do that, but I can't. It's a risk. And I think to myself, you're 22 years old or 25 years, what risk could you possibly think that you're taking by trying to start a business? Like, the consulting company will still be there after your business fails, right? So you might as well.
It's so hard to see that though when you're 22. It's so hard to see that when you're 22. But once you're past that, you're like, what do you have to lose? Like, give it a go.
Yeah. Literally, you own nothing. You have nothing. You might as well just try it. And the experience is worth it. 2-3 years trying to launch a company, if it doesn't work out, is really valuable experience anyhow. And then you can go back to that path that you had laid out, and that's still there waiting for you. So that's my 2 cents.
That's great advice.
Well, I wanted to thank you two. I think your story is pretty cool. It shows some of the grit that you guys went through and your adaptability in terms of, we're going to go this way, but let's go the other way. And you gave the entrepreneurship a shot, adjusted, and AEC industry pace later, a couple of years later.
17 years.
But I think that's so cool because you can see the impact that your special solutions have in the industry and that you've carved out. So I really appreciate you coming on and talking about your story and how different things can get solved in different ways. And even for engineers looking for career paths too, showing them that there's so much opportunity, like you were saying. So definitely appreciate it.
Yeah, thank you guys. Great talking with you.
Thanks for having us. It was really great chatting with you.
Thanks a lot.
I hope you enjoyed the episode today. We'd love to hear your feedback, comments, and/or questions. To leave them, please visit structuralengineeringchannel.com. There, you'll find a summary of the key points discussed in today's episode, as well as the links to any of the resources or websites mentioned during the episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you the best in all of your structural engineering endeavors.